So we are continuing the lecture on hash tables, and as we have seen last time that hash tables are another way to implement a dictionary, and we are looking at them because we want to see if we can achieve better performance than the performance we have achieved using balanced binary search trees. And we said that we wanted the hash tables to give us a complexity of big of 1. And we kind of said, we speculated and said it's not really possible to have a guaranteed complexity of big of 1. And that's because of things that we are going to see today. So hash tables are used for their practical complexity or expected complexity more than their guaranteed worst case complexity. Okay, so in the last lecture we have mostly seen like what does it mean to be a hash table. We said it's an array together with a hash function. And we have talked about this hash function and what they do. They take a key and they give us an index. So when we insert, we get the key of the element and find an index using the hash function and then putting the element in the slot returned by the hash function. And when we look up, we again look at the hash function and ask by giving a key, and the hash function returns an index, and then we go and have a look at the index to look up the element. And we said that the hash function should be efficient, should be computable in constant time in order to give this nice average case complexity that we want, an average case complexity of big of 1. We also talked about a very important property that the hash function must have this uniform distribution. Basically, all the slots in the hash table are equally likely, or all keys are equally likely to be mapped to any slot in the hash table. So basically, the hash function at the end, we don't have this clustering. We don't have all the keys mapped to one slot or to very few slots. We want the keys to be uniformly distributed across the table. And we said that the ideal hash function is the one which provides, or the one which provides us with a one-to-one mapping. So every key maps to a unique slot in the hash table. And then we said that it's hard to have this ideal hash function. It's hard to have a hash function mathematically that is going to map a key or doesn't map two keys to the same slot in the general case. Most importantly, some dictionaries are large and you cannot put them all in the same hash table by having the one-to-one mapping. So if a dictionary has 1 million items and the hash table is 100,000, obviously some elements are going to clash. This clashing, we have called it collision. We said keys are going to collide inside the hash table. And these collisions are going to affect our wished for complexity. We said the complexity of operations that we want is big of 1 because we compute in big of 1 and access in big of 1. We compute the hash function in big of 1 and perform an array access in big of 1. But this performing an array access in big of 1 actually is not really as nice as this because of collisions. Collisions are going to cause us to do other things before we actually can reach the element that we want. In this lecture, we are going to see how these collisions are handled in a hash table. So when you have more than one key mapping to the same slot, what are we going to do? If we have key 1 and key 2 mapping to slot 4, obviously we cannot just cram them in the same slot. We have to have a mechanism. We have to have a way of how we are going to organize these collisions. This is exactly what we are going to see in this lecture. And there are two main strategies that we are going to see. One is called open hashing, and one is called closed hashing. So open hashing and closed hashing are strategies for tackling the problem of collisions in hash tables. Okay, so this is what we have seen, and this is our next step. how do we handle the case where more than two elements map to the same slot? So we're going to start with open hashing. Basically, in open hashing, if we have two elements which collide in the same slot in the hash table, we are going to build a linked list of these two elements. For example, this is a hash table of elements which collide. So this is a hash table. This is the hash, the array, which is the hash table from 0 to 4. So it has 5 elements. 4 and 9 are two keys which are mapped to the same slot. So they form a linked list. And these elements are also mapped to the same slot. So they also form a linked list. So elements 4 and 9, they map to the slot 4 and they form a linked list. Elements 12, 7 and 2 map to the slot 2 and they form a linked list. This is what is open hashing. Now this is now the whole hash table. Okay? So open hashing is a collision resolution scheme. If we have a collision, how do we do it? So 4 and 9 collide, so they form a linked list. Elements 12, 7 and 2 collide and they form a linked list. So how is this linked list formed? Let's look again at the example. We have this dictionary here that we want to insert inside the hash table according to this hash function, which is h of k equals k modulus m. Okay? Modulus is the natural number division, is the division of natural numbers. Okay, so quick check again, is the division of natural numbers. Okay, so quick check again, what is 1 modulus 4? What is 1 modulus 4? And what is 3 modulus 4? And what is 5 modulus 4? And 6 modulus 4? Right. When we divide a natural number by a natural number, we have a result and we have a remainder. When we divide 1 by 4, the result is 0 and the remainder is 1. Because 1 equals 0 times 4 plus 1. Okay? So I think university students should know about remainder. So 1 modulus 4 equals 1. 2 modulus 5 equals 2. 6 modulus 3 equals 0. And 6 modulus 5 equals 1. And 8 modulus 6 equals 2. And so on. So we have a dictionary in front of you, 9, 2, 4, 7, and 12. The dictionary 9, 2, 4, 7, and 12. And we want to insert it in the hash table according to the hash function k modulus m. M is the size of the hash table, which is 5. So m equals 5. So what we are going to do is we are going to insert 9 first. So we are going, because it's a hash table, the key must go through the hash function first. So 9 modulus, the hash function is the key modulus m. So the key 9 modulus 5 equals 4. So the hash table is going to look like this. So this is 5, this is 4, and this is 9. This is the first insertion, because 9 modulus 5 equals 4. And then 2 modulus 5 equals 2, and this is 2, and we have 2 here mapped to it. 4 modulus 5 equals 4, so 4 is going to collide with 9, 4 must go in this place. The element 4, the key 4 is going to collide with 9. So what do? We are going to create a linked list of the two items. Now, basically we are going to insert this element inside this linked list here. Insertions in a linked list can happen. The normal, usual, general insertions they happen at the beginning of the linked list or at the end. At the beginning they take constant time. At the end they take constant time if you have a pointer to the tail. Here we're not going to assume we have a pointer to the tail. Basically we have a pointer to the head, and so we are going to perform insertion at the beginning. So what happens is that the head, and so we are going to perform insertion at the beginning. So what happens is that now this has 4 and 4 maps to 9. Okay. So this is what we see here anyway. So we had 4, we had 9 before, and then we inserted 4. So now we have the linked list 4 and 9. And the first item of the dictionary was 2, and then we inserted 7, and then we inserted 12. Okay? So this is how insertion is performed when we have collisions in an open hashing scheme. Now, open hashing is called open hashing because we are opening the table with linked lists. Okay? This is why it's called open hashing. We are opening the table with linked lists to store the keys which collide. Now, if I ask you, let's say I want to search for the item number 2 or for key 2, what's the complexity of doing that? What's the complexity of searching 2? In order to answer a question like that, you have to decompose the whole operation into small parts. So the first thing we have to do is pass 2 through the hash function. It will give us the index 2. This is in big O of 1. And then we have to perform an array access at 2. This is another big O of 1. And after that, now we are here. What are we going to do to search for 2? We are going to perform a linear search. Okay, we're going to perform a linear search of this list until we find until we find the element that we want. Now, what is the complexity of performing this linear search? Okay, we said the dictionary has n elements. So the size of the dictionary is n. Now, do we have n elements here? If we have a bad hash function such that h of k equals 2, then all the dictionary elements are going to be here, correct? Correct or no? If we have a bad hash function like this, h of k equals 2, then all dictionary elements are going to be mapped to the same array slot. In which case, doing the linear search is going to be big O of n. However, we said that we assume that the hash function has got a uniform distribution. Now, in this case, what does it mean to have a uniform distribution? In this case, it means that the number of keys which collide in every slot is almost equal. Okay? So a uniform distribution means the key slot is almost equal. Okay? So a uniform distribution means the keys that collide here are almost equal to the number of keys that collide here, almost equal to the number of keys that collide here, almost equal to the number of keys that collide here, almost equal to the number of keys that collide here, and so on and so forth. So if the keys that collide in a particular slot are equal to the number of keys that collide in another slot, what does this tell me about these linked lists, the size of these linked lists? In other words, if the size of the dictionary is n and the size of the hash table is m, what is the average size of the linked list? If that was 100 and that was 20, what is the size of the average size of the linked list? The average size of the linked list in this case is going to be 5, because we have 100 elements and they will be evenly distributed. This is the property of the hash function, evenly distributed across the slots. So we have 20 slots, so we put 5 in each of them. This is a good hash function which has a uniform distribution. So every 5 keys map to the same slot, every 5 keys map to the same slot. 100 keys map equally likely to 20 slots. So if I said the average is 5, what is 5 in terms of 120 is 100 over 20. So the average size of the linked list is n over m. So the average size of the linked list here, given a good hash function, is big O of n over m. That's the average size. So again, the complexity of performing lookup, we said we have to compute the hash function position, which is big O of 1. Then we have to do the array access in big O of 1. And then we have, in the worst case, to traverse n over m elements of the linked lists, assuming a good hash function. If it's a bad hash function, this becomes what? Big O of n in the worst case. However, we don't consider that because we assume we have a good hash function. This is called the load factor. This is called the load factor of the hash table, which equals the size of the dictionary over the size of the hash table. They're not equal all the time. Okay? Most of the time the dictionary is larger than your hash table. So in order to, we said our objective of using hash tables is to have a big O of 1 complexity for dictionary operations on average. So in this case, in order to get big O of 1, we said insertion is big O of 1 because all we are doing is computing the hash function, getting the index, accessing, and then performing insertion at the beginning of the list, which is big O of 1. So insertion is big O of 1, which is better than AVL trees. However, now for lookup, in order to have a good performance for lookup, if n over m is good, is a small number, then performance is good. Remember, then performance is good. Remember, performance of lookup in AVL tree is log n. So if you have a dictionary of 1 million elements, if you have a dictionary of 1 million elements, one lookup is going to be the log 2 of that, which is almost like 20. If you multiply that by any kind of constant factor, whatever, it's going to be 20, 40, or something around this number. So if the size of the hash table in open hashing is, let's say, 20 times smaller, or 10 times smaller, 50 times smaller than the dictionary size, then we will have a performance better than the AVL tree or equal to the AVL tree. If the dictionary is 10 to the 6 and the hash table is 10 to the 5, then on average, with a good hash function which basically satisfies uniform distribution, we have 10 steps. Or maybe 12, like constant access, constant for the hash function. If it must be efficient to compute, otherwise it takes more than a constant step, and then about 10 steps traversing traversing the list, the linked list in the worst case. So as you can see, there are lots of practical constraints that must be satisfied in order to get the expected performance of big O of 1. Okay? So hash tables do not have a guaranteed worst case complexity. We use them for their average case performance. So if we choose the hash table size, the closer it is to the dictionary, the better, obviously. If the load factor is the smallest possible, the complexity is the best possible. If alpha is 1, then obviously it's one step. If alpha is 1,000, then in the worst case it is 1,000 steps given a hash function with uniform distribution of keys. Right. So, and deletion is follows the pattern of lookup. Okay, deletion also follows the pattern of lookup. Basically, we have to look for the item and then delete it, and we know deletion in a linked list as is basically removing the pointer and creating a pointer. So it's not a big deal. So it's constant time. The other strategy, other than open hashing, is closed hashing. Okay. There's no point in starting this now, so we get our break. It's 12:23. We should be back at 12:47. Or how much? 12:53. Sorry. Plus 30. Yeah. So we'll be back at 12:54. So see you later.